Okay, so how is everyone today? Wet? Yeah. Happens. All right. So where are we? We had. All right. So that's where we pick up. So if I gave you a number, and I said, does this number have an additive inverse? Then does it?
Yes.
It does. All numbers have an additive inverse. Then what's the formula for computing an additive inverse? So like, what's the additive inverse of 5? Negative 5. Why is that? Right. Because when you add 5 and negative 5, you get 0. And that's significant because 0 is the additive identity. Similarly, if I gave you a number and asked, does this number have a multiplicative inverse? So do all numbers have a multiplicative inverse? No, not all of them, right? So which numbers do?
All numbers except 0.
All except 0, right? Because the thing is that if I give you a number and I say, you know, two numbers, say x and y, how do you tell if x and y are multiplicatively inverse? You multiply them, and you're looking for
The
multiplicative identity, which is 1, because multiplying with 1 is the same as doing nothing. All right, so 0 can't have a multiplicative inverse because there's no x such that 0 times x is 1. So there can't be a multiplicative inverse of 0. Fine. But we're interested specifically in composition. We're interested in composition of what kind of things do you compose? So like you add numbers and you multiply numbers. But what kind of things do you compose? Functions, right? You compose functions. So, well, what's the name of the identity of composition? ID, right? And then whatever you want to call it. Some people just literally call it identity. So then, what's the formula for ID of x? ID of x is x. So the identity function is the function that you put an x in, and x comes right out on the other side. Nothing happens to that x. Fine. So if I gave you two functions and said, determine if these are composition inverses, then what would you do? So what do you mean? So if I said, check if these two numbers are additive inverses, what would you do? Add them and check if you get 0, which is the additive identity, right? I keep saying add, right? And if I say, if I give you two numbers and I say check if they're multiplicative inverses, then you would multiply them and see if you get the multiplicative identity, which is 1. So if I give you two functions and ask if they're composition inverses, then what will you do? Compose them and check if you get id, which is the composition identity. All right. So today, what we're working on right now, oh yeah, that's the last thing, is that if I give you a function, do all functions have a composition inverse? No, not all of them. Which ones do? The injective ones. Only the injective ones do. So, you know, if I gave you a function and said find its composition inverse, then the first order of business is to check and see if it even has one. Because if it doesn't have one, then the correct response is to say it doesn't have one. That's the response that we're looking for. So, injective. So visually, that's the horizontal line test. So like parabolas do not have an inverse. They don't have one. So here we are. Oh, by the way, I wanted to mention that you know, basically every human culture counts in base 10. Like basically just about all the ones that exist now and all the ones that are any recorded history, they all essentially count in either base 10, base 20, and in some cases there's a mixture between like Sometimes there's an admixture of 60. 60 sometimes shows up there. But why does everyone like 10? Is there like something special about 10? Or, yeah, 10 fingers, right? 10 fingers. And so when you write the number 25, what that really means, 25, that really means 2 10s and 5 1s. That's what that means. So 10 plus 10 plus 5, right? And then if you ever come to a place where, if you get interested in math or computer science or something like that, and you want to start counting in bases other than 10, it could happen. Then you'd write down 25. If you meant it to be interpreted in base 10, then you'd write it like that. So that is to say 25, where we're talking about base 10. But what if you take 25 and you do it in base 8? So the way it works, what that 25 means, it means 2 10s and 5 1s. So if we want to do it in base 8, we just need to ask how many 8s. How many 8s can we take away from 25? 3 of them, right? Because it'd be 8, and then we can take another 8, and then we can take another 8. That'd be 24. So that'd be 3 8s, and then 1 1. So as a result of that, you can write the following, that 25 written in decimal is equal to what when you write it in base 8? How many 8s? 3. So it would be, in fact, 31 in base 8, because there's 3 8s and then 1 1. So now base 10 is called decimal, because you've got, deci is the prefix that means 10, and then base 8 is called octal, because oct means 8. So in some circumstances, and instead of writing 25 and then subscript 10, sometimes you write a dec like that for decimal. Dec 25 would be the same as octal 31. And that right there is the reason why mathematicians can't tell the difference between Halloween and Christmas. So Merry Christmas. Because it's Halloween. All right, good. Now that we're past the important bits. Okay. Good. Fine. So here's the question. I could say, how about let f of x be this, be 4 multiplied by x minus 2, cube that, and then subtract, and then I'll do another subtract minus 5, like that. So first question, does f have a composition inverse? So that's the first question. 2, so if it does, then find it. So the name of the function that is the inverse of f is denoted like that, f superscript -1. So like, for example, the additive inverse of 5 is -5. That's its name. And the multiplicative inverse of 2/3 is 3/2. That's its name, 3/2. The name of the composition inverse of f is written that way, f and then superscript -1. That's how you write it. Okay, so for 1 there, we want to figure it out. Does it have a composition inverse, or does it not? Well, the way to understand the question is you could say, well, if I simplified f a lot, if I said, well, I'll just forget about the 5 for a moment. Suppose I forget about the 5, and then maybe I'll forget about the subtract 2 for a moment. Forget about those also, and then also the 4 there. If we get rid of those things, then we'd just be left with x cubed. We got rid of those things. So what does the plot of y is x cubed look like? So this is something that you're expected to know. How's it look? Yeah, kind of like a parabola, but not, right? Because its left arm is going to be down instead of up. Something like that. So now, that's not the function that, that we're asking about, but it is a related function. So that function, does it have an inverse? Is it injective? It is, because it passes the horizontal line test. So this is injective. So good. So now we need to establish that f is injective. Now, what do we need to do to the formula to make it be f's formula? All right. So here's another plot. And I'll write down f's formula. It would be 4 multiply x minus 2, cube that, subtract 5. Okay, so now we need to figure out what happens when you turn this one into that one. Okay, so this subtract 5. This is some graph transformation. That subtract 5, is it playing with the x's or with the y's? Which one does it belong with? It belongs with the y's. Because if you look at the original formula, look what we're doing with the x. We're cubing it. So are we cubing that subtract 5 there? No, it's not being cubed. So it actually belongs over with the y's. So I'm going to move it over there. And all right, so how about that subtract 2? Does it belong with the x's or the y's? With the x's, right? Because notice that originally we're cubing the x's, and now we're cubing the x minus 2. So the 2 is where it belongs. How about that 4? So is that 4 being cubed? No, it's not being cubed. So we're going to get it to be over there with the y's. And so now the question is that all right, if we do that, then what does all that represent? What does each one of those things represent? So there's 3 different things occurring. So what's this? This subtract 2. So in the first place, is it horizontal or vertical? Horizontal, because it's with the x. And then is it a shift or is it a scale? A shift, because it's add or subtract. So specifically, what's going to happen to the plot? Good. So the plot is going to move right, right 2. And you know, the reason why it's subtract is because from a different point of view, it's not really that the plot's moving to the right. It's not that I grab the plot and pull it to the right. Rather, it's that I just hold the plot down and move the axis to the left. That's why it's subtraction. Okay, what does this add 5 do? So in the first place, is it going to be a horizontal thingy or a vertical thingy? It's going to be a vertical something or other. And just looking at the plus 5, is it going to be a shift or a scale? It's going to be a shift because it's an add or a subtract. And then, so how is the plot going to shift then? So it's going to have to be up or down because it's because it's vertical. Down. Down 5. The plot's going to move down 5 because, you know, from a different point of view, what you could say it like this. I'm going to hold that plot there. I'm going to just pin it down and then grab the axis and pull it up 5. Right? And so then the plot would have the appearance of going down 5. And then what is the effect of this 4 there? It's a scale. So is it a horizontal or a vertical scale? Vertical scale. So the plot is going to be vertically scaled by a factor of 4. So as a result, you can have a good idea of what happens. So this point right here that's at the origin, it's going to move right 2 down 5. So right 2 down 5, so that could be like 1, 2 there, and then down 5, 1, 2, 3, 4, 5. So it's going to be about right there. And then it's going to be vertically scaled by 4, which is to say it's just going to be like stretched out. The plot's going to be really tallish, like this. So it's going to go up super fast and down really fast, something like that. So now, how about that? Is that injective? It is. So so as a result, so that's injective, and therefore we know that F inverse must exist, which is to say F has a composition inverse. So in a math class, and anything that uses math a lot, like engineering and physics and things like that, you're always really interested in whether or not something exists, because the thing is that statements about the set of the empty set is true. So, for example, UTD has won every national football championship that we've ever participated in. Is that true?
Yes.
Yes, it's true. Because if you say, no, that's not true, then I would say, oh, please produce the game that we lost. And your inability to produce that game means that what I just said is true. So it's also true to say that we've lost every game that we've ever participated in. That's also true. Because you can anything that you say about the set of the empty set, the elements of the empty set is true. So you have to be sure that something exists before you go off trying to find it. Okay, so to actually find the inverse, so we want to find F inverse of x. Well, here's the main idea. I'm going to do it write a very simple example right here. So suppose we have y is 13x plus 14. So what I want you to interpret that as being is that that's a way to turn some x into a y, right? So you take an x, and first thing you do is you multiply it by 13, and then after that you add 14, and then now it's a y. So x is the input and y is the output. But for this formula, can you solve for x? Yeah, we could solve for x. So let's do that. Suppose we solve for x, then we'd have y minus 14 is 13x, and then, y minus 14 divided by 13 is x. So what I want you to observe is that this formula is how you turn an x into a y. That's what that first formula is. And this formula, this is how you could plug in a y, and it would tell you the x, right? So this is how you this one is how you turn a y into an x. So that's turning the machine around and running it in reverse. That's what we need to do for this function. So we're going to take f of x is 4 x minus 2, cube that, subtract 5. And then I'm going to write y is equal to this, like that. And now, in that formula there, we want to solve for x. So, whatever formula it happens to be, you just got to pull out all of your algebraic tricks. Okay, so we want to solve for x. What's the first thing? Okay, good. So add 5. And then divide by 4. So you can see that, we were halfway there, kind of, right there, when we were checking if the inverse existed at all. Okay, so now what? Cube root. So now, to make sure it's clear, what I want you to see is that we're sort of like undoing what f does piece by piece. So what's the opposite of subtracting 5? Adding 5, right? So then on the right-hand side, it's subtract 5, and then on the left-hand side, it's add 5. And, what's the opposite of multiply by 4? Divide by 4. So moving the multiply by 4 to the other side is divide by 4. What's the opposite of cubing? Cube rooting. So this cube, when it moves to the other side, it's cube root. And now what? Add 2. So we'd be here. So add 2, and then this is x. So observe, we were able to solve for x. So you could say, well, if we had a y, that'd be the x. You plug in a y, gives you an x. So now we're going to do one more step. So we're going to swap x's and y's, which is to say that we're going to take that formula where we solved for x, and we're going to rewrite it. But everywhere that we see x, we write y, and everywhere we see y, we write x. So cube root, and it says y plus 5, but I'm going to write x plus 5 over 4. Then add 2, and then the right-hand side says x, but I write y. And therefore, the inverse function, whose name is f superscript -1, is this. So that's the inverse function. Very neat. Any question about that? So now, on a really adventurous exercise, then it could say, and go on to show that you really have found the inverse correctly by composing it in both orders with the original function f. So you'd go back and say, oh, well, that was the original, and then I'll compose it with that one in both orders. And what should you get in both cases? Which one? Id, right? So you'd get it would be the identity function, which is to say that in terms of the formula, you'd do the whole composition, and the whole thing would simplify down to what? Just x. And it would be really gross looking. So now here's the main idea, to make sure it's clear. So more or less, you're always doing the opposite thing of what the formula says. So this says subtract 5, so the inverse is going to have an add 5. And that says subtract 2, so the inverse is going to have an add 2. This says multiply by 4, so the inverse is going to have a divide by 4. This says cube, so the inverse is going to have a cube root. But there's one other item that basically you have to keep careful track of, and that is that these things occur in a certain order. Right? So that if you wanted to evaluate this formula, would you subtract 5 first? If I gave you an x to plug in? No, you'd have to do that first, right? Because of the order of operations. So those operations have to occur in a certain order. And in the inverse function, they have to occur in the reverse order. It would be just like, if you were getting ready for like a really serious winter day, and you put on like 5 layers of clothes or whatever, and if you wanted to get undo that, you'd have to take the outermost layer off first, right? You can't start taking the innermost layer off. The clothes don't work that way. You have to do them in the reverse order that you put them on. So notice that the first thing you'd have to do is subtract 2 for f. For f inverse, the last thing that you do is add 2. Good. Any question about this? Okay. So now let's do the next thing. So now we get to move to an exciting section. So this is section 5.1. It's called Quadratics. So first, this is a repetition of something we've already said. So a quadratic in variable x is an expression of the form ax squared plus bx plus c, with a is not 0, and a, b, and c are some constants. You know, so we've seen lots of quadratics over the course of the semester. A quadratic function is exactly what it sounds like. It's f of x is equal to a quadratic. And again, a, b, and c are constant. 3, the standard quadratic. In a sense, the simplest one is this one, y is x squared. Or if you like, f of x is x squared. So that means, you know, a, b, and c are 1, 0, and 0 respectively. So a is 1, b is 0, and c is 0. This again is something that you're just expected to memorize. So the as a plot, I mean. So the plot is the standard parabola. So we know about graph transformations. And what we're going to talk about right now is we're going to do graph transformations of this quadratic. So notice that that quadratic has a lowest point. Its lowest point is right there, sitting at the origin, the place where water would sit, you know, if it was raining two-dimensional water downward. So that point is important enough to have its own name. It's called the vertex. And if we do some horizontal and vertical shifts, then all that's going to happen is that this quadratic is going to move around, and its vertex is going to move around with the whole thing. So, for example, I could say, what about this function? G of x is x minus h squared, and then plus k. So what would that look like? Well, so what I'm saying is, in terms of equations, I'm saying, what if we take y is x squared, which is the standard quadratic. So that's the one that we know and love. It's right there. And what if we do the following? What if we say, all right, let's mess with it, and it becomes this. So let's try and consider what happened. So originally we were squaring x. Now what are we squaring? X minus h. Okay, so that h really does go with the x. Does the k go with the x? It doesn't, right? Because that k is not being squared. So let's move it over to be with the y. So that equation is the same as this equation. Y minus k is x minus h squared. All right. So there's two things occurring here. What does that represent? Right. So this is a horizontal shift of h. If h is positive, that means to the right. If h is negative, that means to the left. What does this one mean? vertical shift of k. All right. So what that means is we take this standard plot that you just memorized, and you know, for any hk, what this does is it's saying, oh, just, you know, take the vertex and move it there, move it to hk, wherever that is. So then so, you know, maybe it like this is hk right there. So I didn't draw a scale, so you can't tell me the exact value of h and k, but from the picture you should be able to tell me the sign, the SIGN of h and k. So what's the sign of h? Positive. H is a positive number. How can you tell? Because it's to the right of the origin. And how about k? What's the sign of k? Negative, because it's below the origin. Okay, so then like this. So, as a result of that, we can say that therefore g of x equal to x minus h, square that, add k. That's a quadratic. It's a parabola, and where's its vertex? HK. So it is a parabola with vertex at HK. So as an example, what if I wanted give me parabola P just like G, but I want the vertex at negative 13, comma 14. So what would be its formula? Uh-huh. And then minus 14. All right. So now, you might look at this and object a little bit and say, wait a second, if that says minus h, if that says minus h, and that one says plus k, and those are different, right? That says minus h, subtract h, and that one says add k. Why is it that these are both the same? Why is it that that one is h and that one is k, and it's not one of them is negative or something? Why is that? So what I mean, to give you a different example, if I write this one, if I say y is equal to say x minus 5 square that, and then subtract 9, so there's a thing there. So where's the vertex of that parabola? 5, negative 9. So the vertex at 5, negative 9. So why is it that one of them is treated sort of with a negation and the other one isn't? Is because the 5 is with the x, right? Is the 9 with the x? No. That's actually with the y. So that's the reason why the sign appears to be playing games. The SIGN, the positive negative, seems to be playing games. Okay, last thing before we have a quiz. So what about what if we take the standard quadratic and we look at this one? Say f, big F of x is a multiplied by x squared. So now instead of and this is for some a that's not 0. So now this isn't a shift because we're doing some kind of multiplication. So it's not a shift. So it's some kind of scale. So what I'm asking is that what do we do? What is occurring if we start with this, the standard quadratic, and we do this? Y is a multiplied by x squared. Yeah?
About the example,
Mm-hmm.
wouldn't it be plus 14 since the 14 is plus?
Yes, thank you. This should be plus. This one. Let me do that in red. So previously that was subtract. That should be add, most definitely. I'm not sure what happened to my brain there. Good. Okay, so then now to this one, what is this saying? This is a scale. So is it a horizontal scale or a vertical scale? It's a vertical scale. How can you tell it's a vertical scale? Right, so the question is that a with the x's or is it not? So look at what we're originally doing with the x's. We're squaring it. That's what we're doing originally. And then over here, we've got this, this newcomer, this a. Are we squaring the a? We're not. So it must not be with the x's. So in fact, we want to write it like this. A, and then this is like this. So that would be a vertical scale of a. And as a result, there's two possibilities. There's two possibilities. Is that if a is positive, and more than 1, say, so if it's like 4, then that means it would be 4 times as tall. The parabola would be really tall parabola. If it was positive in between 0 and 1, say like half, then it would be a parabola, but it would be squished. But if a were negative, what would that be? What is a vertical scale that's negative? That's a flip, right? So as a result, we can say the following. There's 2 possibilities. Is that y equal to ax squared and y equal to ax squared. When a is negative, you'll see one thing, and when a is positive, you'll see a different thing. So when a is positive, you'll see a parabola that's scaled like this. So it's like maybe stretched out a little bit vertically. But when a is negative, you'll see this. And one way to remember that is that if you write a less than 0 right there like that, you know, a is negative, it kind of looks like a frowny face, right? And this one is a is positive, and that, you know, that looks like a big old smiley face. All right, so then we'll have a quiz now.